Good evening, everyone. So welcome to my YouTube channel, IITJAM. So today we are going to see sixth lecture on subgroup. Okay. So in this lecture we will study Lagrange theorem. Okay. So what is Lagrange theorem? Let G be a finite group and H be a subgroup of G. Then order of H always divides order of G. Okay. So let me write it in words then mathematically. Then order of H divides order of G. Divides order of divides order of G. So mathematically, what does it mean? It means order of H divides order of G. So let's see its proof. By a previous lecture subgroups, lecture 5, we have G is disjoint union of AH. Okay. Or you can take disjoint union of right cosets. Okay. Same proof will be followed. Okay. Since G finite, we have H is also finite because H is subset of G. Okay. Okay. We claim that order of AH is equal to order of H for all A belongs to G. Okay. H is finite let order of H is M. Okay. So H will be H1, H2 up to HM. Okay. Now here we have HI is not equal to HJ for I and J less than equal to M. I is not equal to 6. Now what is AH? AH is nothing but this. AH1, AH2, AHN. Okay. So AHI is not equal to AHJ because if AHI is equal to AHJ, then what we will have? Will operate A inverse both this side. This implies A inverse AHI is equal to A inverse AHJ. Okay. So what is this? This is identity HI. This is identity HJ. So HI is equal to HJ, which is a contradiction. Contradiction. So this implies AHI is not equal to AHJ for I and J less than equal to M. I is not equal to M. So this implies order of AH is equal to also M. So this implies order of AH is equal to order of H. Okay. Or A belongs to this. Okay. So you first observe as G is finite. Okay. So I will write in a okay. So let's say if let's say it's 2 or let's say it's 1. From 1 we have what is from 1 we have this one A belongs to this AH. G is finite. finite. Okay. So this implies there exists A1, A2 up to A and belongs to G such that because G is finite such that A I H intersection A J H is equal to 5 or I not equal to 0 and G is equal to joint reunion I goes to 1 to N A I H. Okay. Now these are disjoint. So what will be the order? Order of G is nothing but because these are disjoint, the order will be summation. I goes to 1 to N. Order of A I H. So what is this? What is this? This order is equal to H from 2. This is equal to order of H from 2. Now what is this? What is this? This is N times order of H. So we have order of G N times order of H. Okay. So what does it mean? What is the meaning of this? What is the meaning of this? This implies that order of H divides order of, it means order of H divides order of H. So it is proved. So Lagrange theorem is proved. Now we will write corollary of Lagrange theorem. So corollary. Let G be a group and let G be a finite group. Lagrange theorem is proved. Now we move to corollary of Lagrange theorem. Let G be a group, G be a finite group, and A belongs to G. Then order of A divides order of G. So let's see its proof. Okay. G is finite. It means order of G is finite. And okay, order of G is finite. Now consider since A belongs to G, then order of A, yeah, is not equal to 0, because if order of A is 0, then A square, A cube, up to and so on. These are all distinct. These are all distinct. This implies order of G is not equal to finite, which is a contradiction. Okay. Because as A square, A and all belongs to G. If order of A is infinite, it means order of A is 0, then A square, A cube, A and all are distinct and they belongs to G. And G will become infinite set. So which is not possible because G is given that G is a finite group. Okay. So order of A is finite. So this implies therefore order of A is not 0. It means, let's say order of A is equal to M. Okay. Then consider H is equal to E A square A M minus 1. Okay. M minus 1. Then H is a subgroup of G and order of H is equal to M, that is order of A. Okay. It means order of H is equal to order of A. Okay. Now G is a finite group. Okay. And H is a subgroup of G. By Lagrange theorem, we have order of H divides order of G. Okay. But order of H is equal to order of A. Okay. So this implies putting the value of order of H, this implies order of, it means order of A divides order of H. Okay. It means order of A divides order of B. So this is proven. Okay. So another corollary, let G be a finite group. Okay. And A belongs to G. Then A raised to the power order of G is actually identical. Let's prove it. Since G is a finite group and A belongs to G, then by previous corollary we have order of A is not equal to 0 and order of A divides order of G. So put order of A order of A divides order of G. Okay. So put order of A divides order. So let order of G is K times order of A because it divides. Okay. 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 Order of now order of A raised to order of G is equal to we have A is natural number. Now A raised to the power order of G is equal to A raised to the power A times order of A. Okay. So this is A raised to the order of A power A. Order of A is identity because order is a smallest integer such that you raise A to the power that order. What is the suppose order of A is n? It means A raised to the power n is identity. So order if you take order of an element, then you raise that power of element, you will get identity. So it is identity. So it is identity. So A raised to the power order of G is identity for all A1. Okay. So this result is. So today's lecture up to this. If you have any problem related to this, you can comment on my YouTube channel. Like, share, comment and subscribe my YouTube channel. So thank you very much for today's lecture. Thank you very much.